China has a history of pushing the boundaries of innovation, from ancient engineering marvels to cutting-edge military technology. Now, they have done it again, venturing into the world of hypersonic aircraft. The country's new billion-dollar creation is highly exceptional. It threatens to kick other innovations off the chart. But that's not all. It is a technological marvel that could redefine not just air travel, but warfare, commerce, and even space exploration. Ladies and gentlemen, let us dive into the intricacies of China's brand new $13 billion aircraft and explore its promises, its risks, and what it means for the future of aviation. China's aerospace outlook. China's aerospace and commercial space industries have grown at an unprecedented pace over the past few decades, evolving from a state-controlled sector to one that increasingly involves private enterprise. Projections estimate the industry will be worth over $900 billion by 2029, positioning China as a dominant player in the global space race. Historically, China's space sector was primarily led by state-owned enterprises, such as China Aerospace Science and Technology Corporation and China Aerospace Science and Industry Corporation. These companies were responsible for major national projects, including the Tiangong Space Station, Chang'e lunar missions, and Mars exploration programs. However, since 2014, when China opened its aerospace industry to private investment, commercial space companies like Landspace, iSpace, and Galactic Energy have emerged as key innovators, particularly in satellite deployment and reusable rocket technology. The Chinese government has significantly increased its space budget, rising from $2.22 billion in 2022 to $14.43 billion in 2023. This investment is fueling advancements in both state-led and commercial programs. It aligns with China's broader goal of becoming a global space leader by 2045. Meanwhile, regional hubs such as Beijing, Shanghai, and Guangdong are fostering innovation through government-backed incentives and partnerships with private enterprises. Despite its rapid progress, China's aerospace sector faces challenges such as strict government oversight, reliance on state funding, and global competition, particularly from SpaceX, Blue Origin, and ISRO. The country's ability to commercialize its space operations, develop reusable rocket technology, and expand satellite services will determine its future competitiveness. China's hypersonic revolution. China's hypersonic advancements are no longer just about passenger aircraft. They are rapidly reshaping both civilian and military aviation. While Chinese scientists have successfully tested a hypersonic jumbo aircraft capable of flying from Beijing to New York in just 2 hours, they have also been making significant strides in hypersonic weapons. The latest confirmation of a hypersonic air-to-air missile designed to outmatch traditional aerial threats further cements China's dominance in this high-speed frontier. A recent breakthrough in Chinese missile technology reveals just how far the country has come in mastering hypersonic speeds. According to a newly published scientific paper, China has been testing these weapons in specialized arc-heated wind tunnels, simulating the blistering temperatures hypersonic vehicles experience as they cut through the atmosphere. With speeds exceeding Mach 5, these missiles face extreme aerodynamic heating, a challenge that China is overcoming through advanced heat-resistant materials and engineering. These air-to-air hypersonic missiles are not just fast, they are a game-changer in aerial warfare. Traditional missiles operate within a range of a few hundred kilometers, but hypersonic variants can strike targets over 1,000 kilometers away, with speeds that leave enemy aircraft virtually no time to react. This means that China's fighter jets like the J-16 could take out adversaries from a distance previously unimaginable, rendering conventional dogfight tactics obsolete. The hypersonic jumbo aircraft and hypersonic missile program represent two sides of China's grand vision, dominating both commercial aviation and military airspace. The passenger aircraft, developed by Kuikai's team, challenges the very idea of long-haul flights, making global travel an ultra-fast reality. Meanwhile, hypersonic missiles challenge the traditional methods of air combat, pushing global superpowers like the US to rethink their air defense strategies. For instance, the US military's newest stealth bomber, the B-21 Raider, was designed to evade radar and strike deep behind enemy lines. However, the emergence of hypersonic air-to-air missiles means that even stealth aircraft could now be intercepted long before reaching their targets. Unlike conventional weapons that rely on guidance systems and lengthy engagement times, these hypersonic missiles move so fast that traditional countermeasures may prove ineffective. China's hypersonic research is pushing the boundaries of what is possible in aviation, blurring the lines between commercial airliners and cutting-edge military technology. Whether it's making global travel as quick as a short domestic flight, or ensuring air dominance in future conflicts, speed is now the ultimate advantage. With every successful test, China moves closer to an era where hypersonic flight is not just a theoretical dream, but a new reality, one that could transform the skies forever. China's hypersonic aircraft, Nanchang. Imagine boarding a plane in New York and landing in Beijing in just 2 hours. No more grueling 14-hour flights, no more jet lag, just hypersonic speed carrying you across the globe in the blink of an eye. It sounds like science fiction, but China is turning this vision into reality. At the forefront of this revolution is a small but powerful prototype, a hypersonic aircraft designed to push the boundaries of speed, propulsion, and efficiency. If successful, this project could change the way humans travel forever. In a quiet lab in Fujian Province, China, a team of scientists has been working on something revolutionary. Their mission? To create an aircraft capable of flying at Mach 6, which is 6 times the speed of sound. They call it Nanchang 1, a sleek, unmanned hypersonic prototype that could one day evolve into a passenger aircraft capable of traveling anywhere on Earth in just a few hours. At first glance, Nanchang 1 doesn't look too different from other aerospace prototypes. It's compact, weighing just 500 kilograms, 1,100 pounds. But what sets it apart is what's under the hood, a cutting-edge engine system designed to take flight beyond anything we've ever seen before. China's ambitions don't stop here. The country plans to develop a fleet of hypersonic passenger planes by 2035, and Nanchang 1 is the first step toward making that dream a reality. To break the Mach 6 barrier, China had to develop an entirely new type of propulsion system known as MUTR, multi-ducted twin-turbine ejector ramjet, scramjet, a name as complex as the technology behind it. Unlike traditional jet engines, which struggle to function beyond Mach 2, MUTR is designed to seamlessly transition through multiple speed phases, ensuring continuous acceleration from takeoff to hypersonic speeds. At low speeds, Nanchang 1 relies on 2 turbine engines, just like a regular jet. These engines generate thrust up to Mach 2, allowing for runway takeoff, a major advantage over other hypersonic concepts that require rocket-assisted launches. Once airborne, a small rocket engine kicks in, propelling the aircraft from Mach 2 to Mach 4. This transition is crucial, as traditional jet engines simply can't handle speeds beyond Mach 3. At Mach 4, the aircraft activates its dual ramjet-scramjet engines, pushing it to a cruising speed of Mach 6. Unlike regular jet engines, ramjets and scramjets have no moving parts. Instead, they use the high-speed airflow itself to compress air for combustion. This seamless transition from turbofan to rocket to scramjet is what makes Nanchang 1 so revolutionary. It eliminates the need for in-flight refueling and ensures maximum efficiency at hypersonic speeds. China isn't the only country chasing the hypersonic dream. The United States, Russia, and private aerospace companies are also in a race to develop the first viable hypersonic passenger aircraft. The US is investing heavily in hypersonic research, with companies like Hermeus and Exosonic developing supersonic and hypersonic travel concepts. Russia has focused more on hypersonic missiles, but its advancements could eventually extend to aviation. Private firms like Boom Supersonic and Reaction Engines are working on ultra-fast commercial aircraft, though they have yet to reach the speeds China is aiming for. If China succeeds, it could dominate the future of global air travel, offering faster flights than anything available today. With Nanchang 1, China has taken a bold step into the future of aviation. If successful, this aircraft could reshape the way we travel, making long-haul flights obsolete. Military and commercial application. China's hypersonic breakthroughs are setting the stage for a new era in both military dominance and commercial aviation. While the development of a hypersonic jumbo aircraft capable of crossing continents in mere hours is revolutionizing travel, the emergence of hypersonic air-to-air missiles is rewriting the rules of modern aerial combat. These two applications, civilian and military, are deeply intertwined, showcasing how hypersonic speed is reshaping global strategy. The development of air-to-air hypersonic missiles represents a seismic shift in aerial warfare. Unlike traditional missiles that rely on radar guidance and in-flight updates, Hypersonic missiles move so fast that they can engage targets with little to no warning. This makes them particularly devastating against high-value enemy assets like tankers, bombers, and early warning aircraft, which rely on distance and evasive maneuvers for survival. This technology poses a serious strategic challenge for air forces worldwide. Defense systems that once provided ample reaction time against conventional threats are now struggling to adapt. Countries like the United States must develop next-generation detection systems, advanced interception technologies, and electronic warfare tactics to counter this rising threat. Even stealth aircraft, like the B-21 Raider, may become vulnerable if hypersonic missiles become widespread. Military and civilian hypersonic projects share a common goal: mastering speed. The research that fuels hypersonic missile development, such as aerodynamic heating solutions and advanced propulsion systems, also plays a crucial role in building passenger aircraft that can withstand extreme conditions. In many ways, hypersonic travel for commercial use will be an offshoot of military advancements, much like how jet engines first emerged from World War II research before transforming global air travel. Whether in war or commerce, speed now defines the future of flight. Hypersonic aircraft and missiles are no longer just experimental concepts. They are active developments that will shape how we travel, fight, and secure air dominance. With every new test, China edges closer to a world where hypersonic flight is the norm, not the exception. The question now is, who will keep up? The challenges of hypersonic aircraft. It was a vision straight out of science fiction. A jet so fast it could cross the Atlantic in under an hour. The roar of its engines would be unlike anything heard before, cutting through the sky at speeds beyond Mach 6. The world watched in awe as engineers and scientists pushed the boundaries of what was possible. But behind the excitement, a harsh reality loomed. The dream of hypersonic flight came with some challenges. Heat management. At Mach 6, the friction between air and the aircraft's surface didn't just make it warm, it turned it into a blazing inferno. Ordinary metals could not survive. Even the toughest alloys would warp, crack, or simply disintegrate under the pressure. Exotic materials such as ceramic composites, carbon-carbon coatings, and advanced heat-resistant alloys. But such materials weren't cheap. Every new test meant millions of dollars spent on research, and every failed experiment was a costly lesson. Even if the materials could be perfected, there was still another hurdle: the engines. A traditional jet engine simply wouldn't cut it. At those speeds, the air would rush in too fast, choking the engine before it could produce any thrust. The answer lay in scramjets, engines that compressed air at hypersonic speeds before igniting it. But scramjets had never been tested for commercial use. Developing them meant years of trial and error, endless prototypes, and a budget that spiraled into the billions. And even if the aircraft could be built, where would it take off from? Ordinary runways weren't built to handle such forces. New launch and landing infrastructure would have to be designed, adding even more costs to an already expensive endeavor. It wasn't just about speed, it was about reinventing the way aircraft were built, tested, and operated. Operational expenses. Now let's assume the world finally built a hypersonic aircraft that could withstand the heat and had engines powerful enough to keep it in the sky. The next question would be, how do we keep it running? If the word fuel comes to your mind, then just know that it is exactly where the problem lies. Hypersonic aircraft didn't just sip fuel, they devoured it. The energy required to sustain such speeds was immense, and the specialized fuels needed to handle extreme temperatures and pressures were expensive, volatile, and difficult to transport. A single flight could cost as much as a fleet of conventional jets. Then came maintenance. A hypersonic jet wouldn't age gracefully. At Mach 6, every flight puts unimaginable stress on the body of the aircraft. Components would wear out faster, repairs would take longer, and every part replacement would require precision-engineered materials that couldn't simply be ordered from a standard supplier. A hypersonic aircraft can't just land at any airport. It would require longer, reinforced runways capable of withstanding the intense forces of hypersonic deceleration. This means the entire airport infrastructure would need to be redesigned, adding another massive cost to the equation. And what about security? A technology that could make air travel faster also had the potential to be weaponized. Governments would closely regulate who could build, own, or even study hypersonic aircraft. The fear of technology falling into the wrong hands meant companies had to spend heavily on cybersecurity, safety measures, and compliance, all adding to the already staggering costs. Hypersonic flight wasn't just a technological challenge, it was a financial and logistical nightmare. The struggle to mass produce in the future. For hypersonic flight to move beyond top-secret military projects, there was only one way forward: mass production. But how do you mass produce something that barely exists? Aircraft manufacturing had always relied on economies of scale. The more planes a company made, the cheaper each one became. But hypersonic jets required materials so rare and specialized that they couldn't be easily sourced. Components couldn't just be assembled in a regular factory. They needed ultra-precise engineering, cutting-edge manufacturing, and rigorous safety testing before even being considered for flight. Scaling up production was no small feat. Would airlines ever take the risk? Would cargo companies invest in a technology still in its infancy? Would governments allow private companies to take the lead? The answer lies in collaboration. If military forces and private industries could share resources, use the same infrastructure, and streamline production together, then hypersonic flight might have a chance. But even then, one question remained unanswered. Is the world ready to pay the price for speed? Weight limitation. Imagine boarding a plane that could take you from New York to Tokyo in under 2 hours. Hypersonic flight promises to revolutionize air travel, but before it can become a reality, engineers must solve some serious challenges, one of which is weight limitation. Take, for example, speeds beyond Mach 6. Every extra pound matters. Traditional aircraft design principles don't hold up at these speeds, and even something as simple as slowing down for landing becomes a massive engineering hurdle. For a commercial aircraft to be profitable, it needs to carry enough passengers to justify the cost of operation. However, current hypersonic prototypes can only hold around 10 passengers, a fraction of the hundreds that traditional jets transport. Why? Because every additional passenger means more weight, and in hypersonic flight, weight is the enemy. Hypersonic jets consume a huge amount of fuel. The more passengers you add, the heavier the plane gets, forcing it to burn even more fuel just to stay in the air. This makes operating a hypersonic airliner extremely expensive, potentially driving ticket prices into the tens of thousands of dollars per seat. Unlike conventional jets, hypersonic aircraft experience intense aerodynamic stress and extreme heat. Standard materials can't survive these conditions, so engineers rely on ultra-lightweight composites, ceramics, and carbon-carbon alloys. While these materials help reduce weight, they are ridiculously expensive and difficult to manufacture on a large scale. Adding weight also affects structural integrity. The faster a plane goes, the greater the stress on its frame. If an aircraft is too heavy, it risks breaking apart mid-flight due to the immense aerodynamic forces. This is why designers are forced to make trade-offs between durability, passenger capacity, and speed. Hypersonic aircraft must remain light to function properly, which limits the number of passengers they can carry. Building a plane that could soar at hypersonic speeds wasn't just about making it go faster. It meant reinventing aviation from the ground up, designing engines that could withstand incredible temperatures, creating materials that wouldn't melt under pressure, and finding a way to make the entire system sustainable. The landing nightmare. If you think taking off at Mach 6 is hard, try slowing down and landing safely. At hypersonic speeds, the laws of conventional aviation don't apply. A standard jetliner can gradually decelerate using air resistance, flaps, and brakes. But for a hypersonic aircraft, slowing down is a serious engineering challenge. Braking systems that work for subsonic aircraft fail miserably at hypersonic speeds. If a plane traveling at 4,600 miles per hour, Mach 6, suddenly tried to brake like a normal jet, the result would be catastrophic. The sheer force would tear the aircraft apart, and any exposed parts could melt from the heat generated by friction. One effective solution engineers are exploring is adaptive aerodynamics, that is, aircraft that change shape in real time to reduce speed gradually. This involves deploying drag surfaces that create controlled air resistance, adjusting wing configurations to increase lift and slow descent, and using advanced materials that can withstand high temperatures during deceleration. While promising, these technologies are still in development, and testing them requires expensive prototypes and extensive wind tunnel simulations. Aviation noise. For decades, aviation noise has been a public concern, leading to strict regulations and quieter aircraft designs. The introduction of high-bypass turbofan engines and FAA noise certification stages has significantly reduced noise pollution from commercial jets. However, hypersonic aircraft presents an entirely new challenge, one that modern noise control strategies may struggle to contain. They travel at speeds exceeding Mach 5, producing sonic booms far louder than what has been experienced with traditional jets. In the 1960s, the Concorde's sonic boom was one of the reasons it was banned from flying over land, limiting its routes to transatlantic flights. A Mach 6 aircraft would be even louder, with shockwaves powerful enough to shatter windows and cause structural damage if flown over populated areas. Governments have enforced strict regulations on aviation noise, classifying aircraft into noise certification stages under FAA guidelines and ICAO standards. Today's commercial jets meet Stage 4 and Stage 5 noise standards, making them significantly quieter than older models. But hypersonic aircraft with their intense sonic booms don't fit into these classifications, and current noise control methods are largely ineffective at such extreme speeds. Some airports in the 1980s implemented noise insulation programs, using computer models to predict noise exposure and upgrade buildings with soundproof windows, caulking, and baffling systems. However, these solutions were designed for subsonic aircraft. Hypersonic jets would require entirely new approaches to limit their noise impact. Researchers are working on technologies to mitigate the impact of sonic booms, including designing aircraft bodies to reduce the intensity of shockwaves. NASA's X-59 Quiet Supersonic Transport is an example of this concept in action, flying at altitudes where shockwaves dissipate before reaching the ground and adapting FAA and ICAO noise regulations to include hypersonic-specific noise control measures. While progress is being made, no fully effective solution has yet been found. Until hypersonic jets can meet noise regulations, their commercial viability remains uncertain. Without addressing this challenge, they may face the same fate as the Concorde. Limited routes and heavy restrictions. Hypersonic aircraft promise to cut travel time drastically, but at what cost? Unlike traditional aircraft, these high-speed jets operate in the upper stratosphere, where their emissions linger for years, intensifying climate change. While the aerospace industry is exploring alternative fuels like liquid hydrogen, LH2, to reduce carbon emissions, hypersonic flight introduces a new environmental problem: water vapor pollution at high altitudes. In other words, this means stratospheric water vapor and climate impact. Unlike water vapor released at lower altitudes, which dissipates quickly, emissions from hypersonic aircraft remain in the stratosphere for months to years. Studies show that this can lead to stratospheric warming and ozone layer depletion. Here, increased water vapor accelerates chemical reactions that break down ozone, exposing the Earth to more harmful ultraviolet UV radiation. Another major issue is fuel efficiency. Hypersonic engines consume massive amounts of energy, making it difficult to achieve sustainability. Unlike commercial jets that optimize fuel economy, scramjets and ramjets operate under extreme conditions, requiring continuous high-speed airflow. This not only increases operational costs, but also raises questions about long-term resource availability. Unless engineers develop radical solutions, such as advanced emissions control systems, alternative propulsion methods, or new atmospheric regulations, hypersonic travel could remain a luxury with too great an environmental cost. The aerospace industry faces a tough challenge: balancing speed, efficiency, and sustainability in a world increasingly concerned about climate change. The race for hypersonic travel is more than just an engineering challenge. It is a battle against cost, infrastructure, and practicality. On the one hand, the potential is limitless: a world where distances shrink, military response times are cut in half, and commercial air travel becomes something out of science fiction. On the other hand, the reality is sobering. We have a technology so expensive that only the richest governments and companies can afford it. The dream of flying across the world in under an hour is within reach. But whether it becomes a common reality or remains an exclusive, high-cost fantasy is yet to be seen. Now, what do you think? Will hypersonic flight ever become mainstream? Or will it stay locked away in top-secret military projects? Let us know in the comments, and don't forget to subscribe for more content like this.